Sam gave me 30 minutes for presentation. I want to present using these 30 minutes. Thank you very much for introduction. Today, I want to show you the interfacial importance of 0 to 2D in solid carbon nanospaces. It doesn't work. Okay. Here, I'll show you the collaborators on these topics. Many collaborators support this research. Of course, we need to promote the renewable energy technology and also the energy saving technologies. In those cases, we need zero-dimensional to two-dimensional nanospace materials. Here, I want to show you zero-dimensional nanospace. This is a hole in the graphenes. This is what we call this structure is nano windows, because often in the literatures, this structure is called nanopore, but this is not the nanopores because the function is very different of these nano windows. At first, I want to mention this one. The right side figure shows the typical adsorbed state of molecules in pores. The pore has a function for storing of the molecules and ions. On the other hand, nano windows, as shown here, that's just accept single molecule or a few molecules or ions. And this is very different from the function of the pores. Then often we recommend this structure should be named the nano windows. This nano window can distinguish and recognize the molecules. So very unique function this nano window has. And also surface process is different from the nanopores. Here I will show you. This is the nano windows and the graphenes. The graphene, of course, has no carbon structure. Then interaction potential with the molecules, they're not so high with the planes. Then molecules come from here, then must conquer this energy barrier to be accepted to this or trapped by these nano windows. So very different from the nano pores. Then this nano windows and graphene has a very unique function. We recently elucidated this nano window in graphene is a very promising for air separations. Using the different size of the nano windows, these nano windows are thermodynamically stable at ambient conditions. Then this nano window rim has the oxygen or hydrogen. Then we examine the permeation rate by use of the molecular dynamics for different nano window sizes from 0.257 to 0.378 nanometers. Could you see these nano windows? Window size 0.2373 nanometers, smaller than even the oxygen. However, we take into account beam motions, then oxygen can permeate through very small nano windows. This is a result. Permeation of oxygen is much larger than nitrogen and argon. But other larger one, the oxygen, nitrogen, argon can permeate, then selectivity not so great, but the very small nano windows, for example, the 2.73 angstrom, 0.273 nanometer case, permeation rate, 10,000 GPU, very huge, keeping the high selectivity 20. So very great the possibility or promising if we apply the graphene to design the air separation film, very, very promising, but of course, not so easy. Why the oxygen can be permeate by very small 0.27 nanometer window? Because the oxygen or hydrogen can do concerted motion to give the permission of the oxygen, the permeations. Then this we can get high selectivity by this graphene, the nano windows in graphene. This is very important. And also in case of 1D and 2D nanospaces in nanoporous materials, also quite important, as you know, because they have very high surface area and very nice tunability of the porosity. And often we can control the morphology to obtain the better engineering. So 1D, 2D nanospaces, nanoporous materials are very, very important for promotion of the renewable energy technology and energy saving technologies. Here I will show you some example of the 1D pores and 2D pores. And here I want to compare representative nanoporous materials, zeolites and carbons, MOF, zeolites, silica. But in these comparisons, the nanoporous carbon have the very unique properties. In particular, carbon has high electrical and thermal conductivities. Then this carbon nanoporous carbon has a very nice important role in the energy saving technologies. And also I want to add another important point of the nanoporous carbons. This structure is the graphene structure. This graphene has the most strongest dispersion interaction potential per unit weight. So this is very important. And also, of course, it has a very large surface area, 2,600 square meter per gram. But dispersion interaction is short range interaction. Then we need the nanostructure. Here I want to explain. This is the carbon surface. Here is the molecules. The monolayer position molecule can strongly interact with the carbon surface as shown here. But the molecule in fourth layers, interaction potential almost negligible. If the molecular size about the 0.3 nanometers, so at least 1 nanometer scale structure is very important. In particular, this kinds of pore structure is very important. If we have the very narrow pore systems, interaction potentials from both sides overlap each other to give the very deep interaction potential, then giving the very unique function of such a nanoscale pores. So today I want to introduce the materials formation of super high pressure phase in vacuum, and also highly selective absorption of oxygen-18 from oxygen-16, and image charge effects on concentration of core ions. So at first, the potassium iodide case, the literature mentions in order to get high pressure phase of potassium iodides, compression under 1.9 gigapascal, huge compression pressure is necessary. But we introduced the potassium iodides through nano windows in single carbon nanophones in vacuum, not high pressure. Then we can obtain this kind of lattice formation inside the single carbon nanophone, and also we can obtain this kind of synchrotron X-ray diffraction patterns those X-ray diffraction patterns and also this image can be assigned to the high pressure phase, slightly deviated. We didn't apply 1.9 gigapascal, but high pressure phase can be produced inside single carbon nanopore. So this is a representative high pressure effect. Another next one is sulfur. So bulk sulfur is a representative insulator because the unit structure of sulfur is 8-member ring of sulfur. But if we compress by 90 gigapascal, this 8-member ring sulfur is dissociated to form this kind of two-dimensional structure, then giving the metallic properties. And also theoretical work, they predict, if we can predict, if we can prepare the zigzag chain or linear chain of sulfur, those, the one-dimensional sulfur should be metallic. Then we challenge this subject. We introduce the sulfur in vacuum, inside single carbon nanotube and double carbon nanotube under vacuum, not high pressure. Then we can get these kinds of TM images. Could you see this one, double carbon nanotube, 0.68 nanometers? You can see the zigzag chain of the sulfur. And also 0.60 nanometer, more narrower double carbon nanotube case, we can see linear form of the sulfur chain, sulfurs. So we didn't apply the high pressure, but we can observe single chain of 1D sulfur and the linear zigzag and linear form of the sulfur. And surprisingly, we can observe the synchrotron X-ray diffraction of this completely one-dimensional sulfur atomic change. This is double carbon nanotube case. This is the sulfur chain and also sulfur chain. These are zigzag. This is the completely linear form. Then this, the peak position give the bonding distance of the sulfur, 0.192 nanometer. This is slightly shorter than the bonding distance observed in organic sulfur compound. How about the electrical properties? Electrical resistivity of the sulfur inside single carbon nanotube case is very low compared with without the sulfur. So sulfur should be metallic, and also careful examination of the Raman spectroscopic examination give this sulfur should be metallic. Still, we need more study. And also the Professor Keith Gavin's group, they give the theoretical support. The sulfur should, inside single carbon nanotube, should be metallic. And next, the subject is highly selective absorption of action 18 from action 16. We have the several difficult issues in physical absorption still. One is the very difficult to introduce predominant physical absorption of supercritical gases, such as hydrogen. This is very important, but very difficult. And another one, selective physical absorption of isotopic molecules, because the isotopic molecules have the same electron structure, so same dispersion interaction, very difficult to distinguish, to have the selective absorptivity. However, the relatively recently, theoretician Binik predict using the quantum fluctuations for very light isotopic molecules, the quantum molecular sieving effect should be observed. And also later, the Carl Johnson, using the more rigorous theoretical theory, and then also support the Winnicker's prediction. Later, we give the experimental evidence for quantum molecular sieving effects. However, more heavier isotope, action 18 or 16, should be difficult. At first, I want to explain very qualitatively the quantum molecular sieving effect for hydrogen and deuteriums. According to Winnicker's, the quantum fluctuation can be evaluated by the de Broglie wavelengths. Hydrogen deuteriums and de Broglie wavelengths at 77 Kelvin is 0.14, 0.11. The difference is very tiny, 0.003 nanometer, but absorption in 1 nanometer or 0.7 nanometer scale pores, this difference is very important. Here, I want to show you one examples in single carbon nanophones, absorption of hydrogen and deuteriums in single carbon nanophone at boiling temperature of hydrogen 20 kelvins. Smaller fluctuation, heavier deuteriums have the smaller fluctuation, then more deuterium is absorbed, as shown here. The points are experimental one. The curve can be simulated by quantum potential. Then this gives the evidence the quantum molecular sieving is present. But this comes from the translational motions. But how about the more heavier isotope molecules, such as action 18 and 16 or 18? 18 action is very important in medical applications. Positron emission tomography needs action 18. But ordinarily, the separation is quite difficult. Then company must build a very high tower for the separation, and they must wait for a longer time. If we can separate action 18 from 16 at relatively low temperature, because there are many natural gas industries, they have low temperature waste heat at near 112 Kelvin. So if we can separate action 18 from 16 action near 112 Kelvin, that's very helpful. At first, I want to show you the example the results on the carbide-derived carbons. What is carbon-derived carbon? The carbide-derived carbon is produced from the metallic carbide, then the sheet of the metals is derived, then basically carbide-derived carbon consists of the relatively well-developed graphene structure, then more nice pore structure than ordinary active carbon. And also often they have the impure narrow site as shown here. Here, I want to show you such a impure narrow site in TM image. Absorption selectivity of these 18 and 16 of CDC at various temperatures is shown here, 100 Kelvin, 150 Kelvin. 100 Kelvin enough low, then plenty of the internal strong absorption sites for action 18 works. Then longer times the selectivity, high selectivity continue for longer time. And also, how about the effects of the mixed gas compositions? Here, I want to show you such a results, 4.8% to 70%. 70% case, the plenty of action 18. So selective absorption sites are deleted. They are quickly deleted, then the selectivity dropped. But the dilute case, the longer time, the high selectivity occurred. Okay. And here I want to show you the absorption isotomes. Action 18s give the higher absorption amount. And also using such a data, we can get the absorption, isosteric heat of absorption. Then difference is 0.3 kilojoule per mole, tiny, but this is very important because the Carl Johnson applied the quantum corrective nuclear motion mechanism to these action isotope systems to get the absorption. So this nuclear motional energy difference, 0.11 kilojoule per mole, and action 18 selectivity is 1.16. This is very important. So I want to move on the last subject. So last subject associated with supercapacitor. So supercapacitor use the high surface area active carbon, but not sufficiently understood on the ions inside the carbon pores. And in particular, ionic liquids are very important for getting high energy storage than the organic liquid or aqueous ionic the systems. Then for example, Korchunev conglomerates predict some special superionic states should be present in very small carbon pores to enhance the capacitance. Then we need experimental evidence for such a kind of theoretical studies. Then we started the study using EMFI and TFSI, the ionic liquids, using the electron scatterings. We measured X-ray, synchrotron X-ray scattering, but we can get 1D informations, not sufficient. Then we applied hybrid reverse Monte Carlo simulation to obtain plausible 3D structures. Once we can get 3D pore structures, we can obtain anion, cation, the structural informations. Here, I want to show you such a results. Black shows total electron radial distribution functions. Blue shows anion, the electron radial distribution function. This one, bulk liquid case. Bulk liquid case, the anion electron radial distribution function has a negative peak here around the anion. Of course, around the anions, positive ions should be here. Then almost no anions, then negative peak is observed. But in highly confined 0.7 nanometer pores here, this no clear negative peak. Then we evaluated occupation of these parts by cations. The cation occupations in 0.7 nanometer pores, only 76%. On the other hand, anion can occupy 24%. Why? Anion should be repel each other. This comes from the very special reason, because here I want to explain the anion, they have the contact situation as shown here. The anion repel each other, such a repulsive energy plus 12 kilojoule per mole. However, once anion here, electron in carbon walls, they just go away, then positive charge is induced. Then plus image charge can attract this anion. Then such an attractive interaction is minus 21 kilojoule per mole, almost twice of repulsive energy. Then the anion can associate each other in very narrow pore, giving this is some special reason for giving high supercapacitance. So this is just agree with theoretical prediction by Kondrats and Korchinov. They say this kind of structure is super ionic state. In order to confirm this, we apply the electrical potential. Then if we apply +2 voltage, surely anion occupation increase from 23% to 34%. So the carbon pore, electrical conductive pore space are very unique. They have a very unique ionic structure. This is very important, the behavior. So I want to finish. We can choose solid nanospaces of different dimensionality considering our purpose. But we are very happy to challenge future research subjects which shall be waiting for us. So there are so many unresolved issues. Thank you very much.